Multiple sorting algorithm arrange the data in ascending or descending order. And in this course, we will be discussing the selection sorting algorithm. We will discuss the logic behind selection sort along with its implementation in Java programming. Analysis of the algorithm concerning time and space complexity will be carried out to explore its potential applications. So this course will be beneficial for optimized programming and a better understanding of sorting algorithms. Stay tuned with us if you want to know more about selection sort in Java, and we will break it down for you in this session.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. As it said, knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I will definitely respond to your comments. Hello everyone, welcome to the session where we'll be talking about selection sort in Java. Before proceeding ahead with the complete course and the session, let me tell you what all we are going to discuss in the session. So we'll be talking about the selection sort algorithm. Among various available sorting mechanisms, sorting algorithms, one of it is selection sort, about which we'll be talking about in the session. And then we'll go ahead and implement the selection sort algorithm in Java programming. And lastly, we'll also do the time and space complexity analysis for a selection sort algorithm.
Selection sort algorithm. Now let's talk about what is selection sort. Now before we move to this sorting algorithm, let's try to understand what is sorting. So if you have a bunch of students, and out of those bunch of students, let's suppose some of them have either left the college or school, or they are absent. Right now you want to arrange the remaining students either in ascending order or in descending order. So for that reason, you might require sorting. So this is one of such sorting algorithm wherein which helps us to sort elements or number of students. It can be any object, right? So it is a simple sort algorithm that revolves around the comparison. So now this is different from if you talk about bubble sort, insertion sort, and selection sort. This sorting algorithm is predominantly based on comparison, right? The comparisons are done more as compared to swapping. In each iteration, one element gets placed, right? If you think about bubble, how it worked like a bubble, and at the end you had your element fixed at its original position, which was at the end when we are trying to sort our array in the ascending order. Now, in the same fashion, right? In this sorting algorithm, one element that can be either the largest element or the smallest element. So we are going to put in the case wherein we will be dealing with the smallest element. In each iteration, the smallest element get its placed fixed in the original array. That means when we sort the array wherein this element belongs, that is the least element that is on the first index, right? So this element will have its position after one iteration. We will be choosing a minimum index in this sorting algorithm. We have one minimum index, and that can be named as minimum, right? Since we are dealing with the smallest element. So now that minimum element in the array is placed at the beginning, right? Beginning of the array. And later on, we will compare it with all the elements and find out the minimum, and then swap it with the first index. Okay. Similarly, we are going to do for all the rest of the elements. Okay. Now, this selection sort is basically selecting an element, that is the minimum element, in each iteration and placing it at the appropriate position. So that is the basic logic behind what selection sort. Now let's talk about selection sort algorithm. Now in this algorithm, our main objective is to find the minimum index, right? So let's suppose if we have one array. Now in this array, there is one minimum index. Let's suppose that it is at the first index, right? Since we are keeping in mind, right? I told you at when we talked about what is selection sort. At that time I told you that we can have two cases. Either you can pick up the largest element and fix its position at the end, or you can pick the minimum element, that is the smallest element. Okay, so in this case we will be dealing it with the smallest element, right? Now this is our minimum index, right? This is the 0th index. Now this outer loop will work from 0 to n minus 1. Now why n minus 1? Okay, I will tell you why. Because then what we will do, the next step is that we will have this minimum index, right? And it is pointing to 0 in this case. And our iterator, that is I, will start from this position. Then in the nested for loop, that is, again, this is condition where we have one for loop and inside that we have another for loop. That is what you mean by nested for loop. Now, since it is a comparison algorithm, what we are going to do inside this sorted part, or inside this unsorted part that is there, what you can say, the rest of the elements. Okay, so we have this j iterator which is pointing to I plus 1. That means we will not compare. It doesn't make sense, right? If I and j are at the same position and we are comparing them, it doesn't make sense, right? So we have this j placed at this iterator at this index, right? 1. This j iterator is at index 1. Now what we will be doing, we'll be comparing it because it's a comparison algorithm and number of swaps are less. That means if there are n elements, there will be n or n minus 1 swaps. Okay, so the swapping is reduced as compared to bubble sort. Okay, so now what happens, we will be comparing them. Okay, and we will be trying to find the minimum index. Let's suppose this is 3 and this is 1. So since 3 is greater than 1, that means our minimum index will be updated. So now our new minimum index is what? At index is the 1, right? This is the minimum index. Okay, done. Now once this comparison is done, right? So again we will check if 4 is less than 1, no. If 5 is less than 1, no. If 6 is less than 1, no. If 0 is less than 1, yes, 0 is less than 1. That means we are again comparing it, right? And we are not swapping them. We will wait once this entire iteration is done. So I will update my minimum index to what? 5, because that is the minimum index. Then we have, let's suppose we have 8. Okay, done. So now once this entire for loop is exhausted, right? Now what we will do, we will swap this minimum indexed element with the minimum index that was earlier there, that is the 0th index. Okay, now we'll swap it with the 0th index. Okay, so now what happened, this we will get here 0 and we will get here 3. So only one swapping is done. So now after first iteration, all the elements will be at its own position, because since we didn't swap any elements, we swapped only a single element, that is these two indexes, that is 5th and 0. Okay, so now what we will have, 0, 1, 4, 5, 6 and 3, and at the end we have 8. Okay, done. And then we will iterate through again. So now our iterator will be here and our j will be here, and this time around minimum index will be, right, earlier it was 0. Now since we will not take care of this, or we will not think about this index now, because this is already at its original position, the element is at its appropriate position. That means when we sort the array, 0 will be at 0th index. So we will not think about it, and it doesn't matter to us now because it is at its original position. So minimum index will be now 1. Okay, so now let's try to see an example wherein we get the better understanding of this algorithm. So if you observe carefully, this is our input array, right? So we have 23, 10, 16, 11 and 20. Now what happens, we'll make this our first step, and this is our iteration number 1. Okay, so now what happens in this, we have our minimum index that is at 0. This is our I and this is our j. Now we'll compare, right? Is 10 greater than 23? No, it is not. So still we have minimum index as 0. Is 10 greater than 60? No. Is 10 greater than 11? No. Okay, now this is the first step. Okay, just a minute guys. So let me erase this. So our I will be here and j will be here, and minimum index is at 0. Okay, because that is the first index. Okay, so since we are taking into consideration the smallest element, so now we'll compare. Is 23 greater than 10? Yes. What we will do, we'll update our minimum. That means this is now index 1. Now what we will do, we'll have our index updated as 1, and then what we'll do, we'll compare 10 with 16, 10 with 11, and 10 with 20. Since this is our minimum index after first iteration, now what we will do, we'll swap it with the first index. That is this, and this element will be swapped. So that is why we have 10 here and 23. Rest of the elements are same. Done. So this is our first step, and our I was at 0. Now our I is at 1. So this is our minimum index, right? This is our minimum index in this case. Now 11, in this case, what is our minimum index? That is 21, right? So min is here and 23. Now 23 will be compared. It is greater than 16. So this will be our min. Again, 11 will be compared. So this is our min. Now 11 will be compared with 20. So this is not our minimum element. Now this is our minimum element, and it will be swapped with 23. So 23 and 11 will be swapped. So that is what you see here. So 10, 11 and 23 is swapped with this. So 23 here and 11 here, right? So 23 will be here and rest of the elements will be as it is. So this is after iteration number 2. Now what happens in iteration number 3? So we have 0, 11 at its original position, right? Now let's swap back and let's erase this. So now what happens? So this is our minimum index, right? And now 16 will be compared with 23, nothing will happen. 23 will become 16 will be compared with 20, nothing will happen. So this is our minimum index, and this is the ith index wherein we will be swapping it. So 16 will be swapped with itself and rest of the elements will be as it is. So you will see 16 and then 23 as it is and 20 as it is, considering this iteration number 1. Okay, so after iteration number 3, this is our input array. So similarly, after third iteration, this thing will happen as 23 is greater than 20. So these elements will be swapped, and in the fourth iteration is required as last element is already sorted. Okay, so no fourth iteration is required as the last element that is there which is already sorted. Okay, so this is the whole demonstration of this selection sort algorithm.
Now let's see the implementation of selection sort algorithm. I'll go directly to the Eclipse IDE and we'll write the code there and see how the implementation goes. So here I've already created a sort class. Okay, in this there is public static void main method also. Now I'll create a method or a function, you can say, for a selection sort, and that method will be called from the main method. Now let's go ahead and write down the code. So public static. I use static keyword every time over here because we don't have to create an object for the class to call this method. Directly we can call the method without using any object for it from the main method. So that's why static here. You can avoid that. In that case, you have to create an object of this class sort and then call the method. Void, because I'm not going to return anything from this function. We'll print the sorted array in the function itself. So let it be void, or you can have return type int, then in array type of a return type. So in that case, you have to return the array. So okay, selection sort. Okay, the input will be here, nothing but an array which had to be sorted. Okay, so selection sort works in a way that it selects the smallest element among the complete elements of an array and places it at the required or the specified location, specified index. Now what is a specified index? Like suppose the array is given, okay, there are 6 elements in an array, so it will start from the first location. For the first location, it will search the entire array and find out the smallest one. Whichever is the smallest one, that will be placed over there. Then it will go to the next index and it will search for the smallest elements again, but in the remaining elements after first, like starting from second to the last index, whichever is the smallest element, that will be selected and will be placed at the first index. Then it will go to the second index. Now in second index also, it will place that smallest element which are there among the remaining element, that is starting from 3 to last. Okay, so that's how the selection sort works, and that exactly, this picture you can imagine and you can write it down, the code for that. So it will start with the for loop. So for int I equals to 0, okay, and I will be less than a1 dot length, okay, and I should be incremented every time. Now inside this, we'll have a temporary variable here also to store the current index being referred. Okay, so let have any uh, intermediate, intermediate, or let it be inter itself. Okay, I think just the name is clear, right? Intermediate variable is your inter I. Now we'll go to the for loop again because we have to find the smallest element among the remaining elements, right? So for loop int of j, which will start from I plus 1 remaining elements, right? And it will go till the end. That is a1 dot length. And we have to increment that also. Okay. Now, in this, we have to check for this, find out the smallest element. So for that, we have to do the comparison. And for comparison, we know what is the loop use, that is if loop. So if a1 of j is less than a1 of intermediate variable, or let's keep a smaller name for this, that will make our things easy. So let be k. Okay, it will be confusing, I think. No. Um, uh, okay, k1, fine, let it be. So k1 is right now the intermediate variable which we are using, or it is keeping track of which index value right now is being referred. Okay. So if this is less than this, then in that case, what has to be done is that your this k1 value will change. It will be now j, right? So that next comparison can start. So ultimately, what will end up with is that once this for loop will end here, right? So once this for loop ends, we'll be having the smallest element at our k1 index. Okay, so k1 index will be pointing to the smallest number or smallest element in the complete array. So once we found the smallest element, we have to swap it from the ith location. Ith location nothing but the current location which is being referred, right? So once this for loop ends, we'll write the swapping code. So I'm using swap variable here. There is a third variable. Using third variable, I'm doing the swapping. You can do it using any other Boolean expression. I mean, arithmetic operators also. Anything is fine, guys. It's not mandatory here, anything. Both will work fine. Now a1 is given to a variable swap. So a1 will be populated with a1 dot k1, as k1 is having the current smallest value. And now k1 is empty. So k1 will be now populated with the swap variable which had a1 I. Okay, so swapping is done. Once the swapping is done, this code will end over here and this function ends here. So before the function ends, let's write the for loop to print this array, sorted array. So I less than a1 dot length I plus plus. Okay, so in this we have to just print the array. So a1 I. I'll just a little bit decorate this so that it looks neat, meaning it will print the output in the same line, nothing else apart from that. Okay, now let's call this selection sort method from the main method. So for that I need an array first, a1, which is equal to new int, and then we'll define the elements here. Let's put it in a staggered way so that once it sorts we get an idea. Okay, let's call now the selection sort here, selection sort for the array a1, right? So yeah, that's it. Let's see if it works fine. So yeah, you can see here 1, 2, 3, 4, 7, 8, and 9. This is our output. So the logic has worked completely fine. And this is the logic, that is, this for loop is going to find out the smallest element among the remaining elements. Once we find it out, it is being pointed by a variable k1. So we'll swap that k1 with the current ith element which is being referred. And once that's the whole process, and we have to perform this whole process from beginning of the array to the end of the array. So for loop for I will go from 0 to end of the array, that is a1 dot length. Okay, and then lastly here I have just printed the sorted array, and from the main method nothing but we called the function directly from here. You can see here I have not used any object of a class because it is a static method and I can call directly without using the object of the class. Okay, so that's all about the Java implementation of selection sort algorithm.
Now let's see the time complexity of selection sort. Now, if you talk about worst case, that is if the array is unsorted or it is we are trying to sort an array which is reversed in nature. Okay, so let's suppose we are trying to sort the array in ascending order and we get the array in ascending order or descending order. Okay, so that is 10, 9, 8, 7, and 6. So this is the worst case, right? And now what happens in this case? Every index, the minimum index will be updated for every element. Okay, so 10 will be compared with the 9, so minimum index will change from 0 to 1, then 0 2 3 and so on. Okay, to find the minimum index, that is this element. So this is the worst case. Now what happens? We have the outer loop that is working from 0 to n minus 1 and the inner loop that is working from 0 from j plus 1 to the size. So in any case, whether we have this unsorted array that is here, we will still be traversing big O of n square times because we have these two for nested for loops which are working up to the size of the array. Done. And same thing happens in the average case as well. Whether we have some elements in the sorted format, let's suppose we have half of the array in this way, and then the rest of the elements are unsorted, still we will not update our minimum index, but rest of the elements will change for the not for these three, but for the rest our minimum index will keep on updating. Okay, so it doesn't matter. So average case type, if you talk about average time complexity, it will also be n square. But what happens if our array is still sorted, right? Or if our array, that is the array given, is already in sorted format, will there be, if we modify our bubble sort, we can get this down to big O of n. But this is not the case in selection sort. Still we will be comparing in the outer loop from 0 to n minus 1 or size minus 1, and in the loop will be again going from j plus 1 to less than size, without, even if we are not going in this for, in this if condition, that is the comparison condition will not be executed and the minimum index will be as it is, still we are going through this for loop. Okay, whether we are not, even if we are not executing this if block, okay, it doesn't matter, still we are going, the n square time complexity will be there even in the best case as well. Okay, so this is all about the time complexity of selection sort. Now let's talk about the space complexity of selection sort. Since we are not using any auxiliary memory, so auxiliary memory can be in the form of arrays, linked list, stack, queues, or even strings. Since we are not using any of these extra memories in order to sort our array, so the reason for that is because we are doing this within the array that is provided to us, right? So the space complexity is constant. That means big O of 1, as we are not using any auxiliary memory. Now let's talk about selection sort analysis. If you observe carefully in this array, let's take an example first: 10, 9, 8, 7, 6. Okay, let me put a 6 here. So this is our array, right? And in this array, what we are trying to do, we are trying to arrange it in an ascending order. So now, if you remember the algorithm, the outer loop worked from 0 to n minus 1, and then inner loop worked from, that means 0 plus 1. That is, let's suppose if this is an I iterator, if we use in outer loop, we used I, and then in inner loop, we use j, then j work from I plus 1 to size, that is n, right? Now, and then inside this we used to compare. So now in worst case, every element was compared, right? J was compared with I plus 1, right? Or I was compared with j plus 1. So it was compared with this, and this. And we were selecting the minimum element in the array, the minimum index rather. We were selecting the minimum index in the entire array. So this was working for n times, and this worked from big O of n times, right? And in worst case, the number of comparisons required will be big O of n square, because we are trying to find the minimum index in the entire array, right? And once we have that minimum index, and later on we'll swap them, right? In worst case, it will go from 0 to n, that means big O of n, and the inner loop will also go from big O of n, that means 0 to n. So in worst case, since these are nested for loops, so the worst case will be big O of n square. And for comparing them, well, I'll always compare all the elements, and it will be again, it will boil down to what? Big O of n square when we talk about number of comparisons. And what happens when we are trying to swap them? Since we have this minimum index that is there, only one swap was required, that was outside this inner for loop, right? So we have this inner for loop, and here we were doing the swapping. In worst case, the number of swaps that are required is big O of n. Okay, in worst case, that means we were swapping only single time, and it will be the case, right, that in worst case that all the elements right at the end will be swapped. So we will have at the end what? 5, 6, 7, 8, and 9, right? And we will swap them only once in the entire array, that is once for every element. So in worst case it will be big of n square. Now, what about stability? If you talk about stable algorithm, it means that if you have this array, let's take an example, it is 10, 8, 9, and 10 again, and then 6. If you talk about this, the stability will boil down to two things: the relative position of these two elements, 10 and 10 dash. Now, if we sort this, it can be 6, it will be rather, it will be 6, 8, 9, 10, and 10 dash, right? So it will be 10 and 10, but just to separate these two tens, we are taking as an example, we are taking this, assuming this 10 to be 10 and this 10 to be 10 dash. And it can also be that it will be 8, 9, and then 10 and 10 dash and 10. So both of these are sorted, right? But if you talk about stability, this is a stable algorithm. Why? Because the relative position of this 10 and this 10 is intact, and this is an unstable algorithm. Now, when we compare or when we do the swapping in selection sort, it is not guaranteed that it will be stable, right? And the elements can be unstable. That means the resultant array will be in this format, that 10 dash may be at first and then we have 10. So it is not guaranteed that it will be always stable, but yes, we can make it stable by modifying our selection sort. But if you talk about traditional selection sort, it is an unstable algorithm, right? Now, what about the in place? That means, are we using any extra memory or extra space? No, we are not using any extra space, right? Extra space can be a linked list, it can be an array, it can be a stack, it can be a queue, right? We are not using any of these extra spaces. So that is for the same reason this selection sort algorithm is an in place algorithm, right? Because we are swapping our elements and we are comparing them within the given array, right? We are not using any extra memory, right? So for that reason, this is an in place algorithm. Let's try to reiterate what we learned so far. So if we talk about number of comparisons, in the worst case, it can go to big O of n square. In terms of number of swaps, it is big O of n. It is an unstable algorithm and it is an in place algorithm.
Now let's summarize the session. So in this session, we discussed about how the selection sort algorithm works. With an example, we saw a step-by-step process, how the given data or given sequence of numbers or characters are arranged in a sorted order. And then after understanding the concept behind selection sort, we talked about its implementation in Java programming. So the complete code we wrote in using Java programming language. Then also the time and space complexity for selection sort was done. That is how much time relatively and how much space it takes for a given n input to perform the complete selection sort. I hope you like the session. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. As it said, knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I will definitely respond to your comments.